don't
He was.
see him anymore.
I'm back?
Here he is. Okay.
Okay, I think it can only take up to 5 people. So I was just saying it's going to be hard because Russ, Jeanette, and Al already tackled all the big subjects. That's it. There's nothing left.
We are going to go back and we will hear your opinions as well. No, okay. I will just pretend that this is a different session. So I would like, of course, to thanks everybody again for attending this and surviving to this workshop until the end, all the audience and of course all the speakers. It's quite late in many parts of the world, so thanks for everybody to be here. And so we can start the final discussions. And I think just as an introduction of what would be the goal of this discussion is that we often hear that there is a significant gap between the tools developed in academia, especially in the last decades with the progress of artificial intelligence and machine learning, with respect to the applications and techniques that are used in industry. Moreover, I think we can probably say that robotic manipulation skills that the scientific community in the overall has developed are still not at the point of being comparable to human-level versatility and dexterity. So what are we wondering and trying to understand in this workshop and with this panel is why there is this gap and what can we really do about it? Well, we already have an excellent group of speakers that with a mix of expertise in between academia and industry. Of course, we have Professor Ted Drake from the Data Research Institute. We have Juan Aperillo Ojea from Radio Robotics, Al Rizzi from Boston University, Matej Ciocarli from Columbia University, and Adam Norton from UMass Lowell. I know that some of you already introduced themselves before, but some not. So would you mind just give 1 minute short self-presentations and so that everybody in the audience know who you are, if they don't already, and then we can start. You can go in any order, otherwise I will call you. All right, I'll go in the order that I see the people on the screen. So Matej, why don't you start?
Sure. Hello, I'm Matej Ciocarli. I'm a professor in mechanical engineering at Columbia University. Before Columbia, I was at Willow Garage, which some of you might remember as a sort of robotics research incubator in Silicon Valley, and then briefly at Google. But now I've been at Columbia about 7 years. But I'll draw on my experience from Willow Garage and Google to try to answer some of these questions. So thank you for having me.
Okay, Juan.
Hi, this is Juan Aparicio. I work at Ready Robotics, leading their product organization. Ready is a startup that is making the first operating system and platform that works across different robotics and automation systems. Before that, I had the luck to lead a team of researchers and engineers at Siemens Technology in Berkeley, California, where we were basically answering the question if deep learning can revolutionize the world of robotics. That was around 6 years ago, and some of the work that we did was published together with professors in Berkeley like Ken Goldberg or Peter Abil or Sergey Levin, and we also work in Stanford with Janet quite a lot.
Al?
I'm Al Rizzi. I'm Chief Scientist at Boston Dynamics. I've been at Boston Dynamics for 15 years. In those 15 years, we were, an independent research and development contract house. We got acquired by Google and shifted out of that business and became, Google researchers looking for ways to commercialize our technology. Google sold us to SoftBank, who really helped accelerate that effort and helped us focus on actually getting initial products out. And then just recently, we transitioned to being 80% owned by Hyundai Motor Group, which we're excited about because it's nice to actually have a parent who knows how to build things. Prior to Boston Dynamics, I used to be faculty in the Robotics Institute at Carnegie Mellon. Adam, over to you.
Hey, everybody. No, I'm coming in kind of at the last session here, but I'm Adam Norton from the University of Massachusetts Lowell. I'm the Associate Director of the NERV Center, the New England Robotics Validation Experimentation Center, supervised by Holly Yanko, noted HRI researcher. I basically run a test and research facility that is all around the development of evaluation methods and metrics for robots of all different types, including manipulation systems, mobility systems, aerial vehicles, pretty much everything except for surgical robots. I also serve on the ARM Institute's Metrics and Evaluation Working Group, one of the co-chairs of that group. And I know Arnie gave the opening statement to this workshop earlier today. And excited to hopefully provide some insight into test and evaluation of these systems.
Russ?
I'm Russ, professor at MIT and the VP of robotics at Toyota Research Institute. Worked on legs for a long time, flying things for a while. Now I'm focused on manipulation.
Thanks. I think the introduction were already very interesting. So I'm excited to start with the actual questions and to hear all that you guys have to tell us. And I think in the spirit of the, well, actually, before starting, I just want to remind to everybody, if someone just joined, that please, if you have any questions, just add them to the chat. Or you can even put yourself on the box on the bottom right and then ask directly your questions. In the meanwhile, I was saying that I think the spirit of the workshop is that the idea behind the workshop is that there is a gap between how industry and academia are tackling robotic manipulation and manufacturing, and that the artificial intelligence and machine learning is playing an important role in this discrepancy. Therefore, I think it's important to start by defining what this gap is before actually trying to get into the possible solutions for this gap. So are academia and industry indeed really taking different paths, different approaches and solutions for robotic manipulations and manufacturing? And can we try to characterize what these differences are? Again, the question is open to all the speakers. And
I'm curious if it would be useful to distinguish between perception ML, has that transferred successfully, and the gap is more on RL for manipulation and control, or is it even a perceived gap on just using ML for perception? I'd be super interested to hear people's thoughts on that.
I mean, being the sort of learning skeptic in the group, I will happily say that we constantly use, ML-based tools for solving difficult vision perception problems, right? And so I think that has become just standard fare as an effective way to encode solutions to that particular class of, and I'm going to call them algebraic problems, right? Because they're one shot. Look at this and tell me what you see kinds of problems for the most part. And I think those, we certainly accept those as being very viable. I think we're still figuring out how to apply RL solutions at a level of trustworthiness and robustness to meet things that we're either able to do demos with or harder yet comfortable actually delivering to customers.
I would also go ahead, Matej, if you want to go first.
Go ahead.
Thanks. So I would also argue, for example, one of the things that I miss from going to actual conference is getting the swag from the conference. So this was from RSS 2017, and it was in Boston, and we were presenting DexNet 2 back then. So Jeff Muller was the main author at Berkeley, and we collaborated with them. I was one of the authors, and that is, for those of you that don't know, DexNet is applying deep learning for grasping. And actually, fast forward 5 years, there is today a startup from the same team of researchers out of Berkeley tackling that problem using DexNet in production, right? So It has transfer. It just takes time, right? It takes time to move from academia into a product that is robust enough that can add some value. And it requires a need, right, in the industry, right? It's not like the problem was not probably there 5 years ago. Now, due to the high demand on intralogistics, these kind of solutions make sense because there is no other methods that can cope with the variety that we see in an Amazon warehouse, for example. That being said, also obviously there is. I also make the case in my talk at this moment that there are current approaches that also work very well, right? And so when we add something new into the mix, it's always important to see, okay, what are the conditions where this method performs better, and compared to something that is already used out there, right? To be fair with the state of the art, right? Because a lot of times when we, for example, in just being very specific on reinforcement learning, when we first started to popularizing it, right, there were a lot of articles saying, okay, this will really solve all the problems in the world, and that's not the case, right? It has a lot of limitations. It's obviously useful, but it has also limitations. So that's the last point. The last point that I want to make also is in terms of cost, right? And that goes to your question, Russ, in machine vision, a lot of times the cost of getting something wrong is not that huge, unless, of course, in autonomous cars you are missing a pedestrian and you hit it. I mean, obviously, but in terms of in manufacturing, I mean, the worst thing that can happen is inspection goes wrong, but it's a more mature field. While if you are manipulating, you can really mess up things, right? Particularly when you are inserting things or assembly, the price of getting that wrong, maybe a completely wrong product that can even explode or have deficiencies along the way. Your entire production line can be stopped because you mess up there. So it's not also a surprise for a lot of people that the first application that all this research is manifesting is with really suction cups, right? Because it's more forgiven, and really the fact that you are missing a picking is not a big problem, right? So these are just 3 thoughts on the topic. Back to you, Martin.
Yeah, and my point was going to be one of your 3, that it just takes time, right? That I strongly disagree with this assertion that academia and industry are looking at things in different ways, and there is this massive gap. We see huge success stories. They just take more time, right? Look at Fetch Robotics. It was acquired last week or the week before. A massive success story, a logistics warehousing robotics company, which was founded by people that used to be at Willow Garage that I worked with, terrific engineers. So what was Fetch their main technology? Autonomous navigation, so SLAM, in warehouses, in semi-structured environments. 10 years ago at Willow Garage, particle filter SLAM was considered kind of known in academia. People weren't really doing the research anymore because it was done. And the whole idea of particle filter based SLAM and probabilistic robotics, when was ProbRob published? At that point in academia, it was already being studied for 10 years before that. So here we are, 20 years after maybe the beginning of probabilistic robotics becoming a big thing and particle filter SLAM becoming a big thing, and it took 20 years for Fetch to become acquired, to be acquired. Look at a torque controlled robot arm, the KUKA lightweight arm. It was 10 years in development in academia, another 10 years, and DLR pushed it in as a research project for 10 years, another 10 years at KUKA. It took 20 years for it to become a successful commercial product. So in that sense, things like reinforcement learning used for motor control tasks. Sure, it's not translating yet. We're not seeing industrial products that use RL, Model 3 RL, for motor control. I'm positive that it will. It just needs more time. Russ, you were asking earlier, you're spending time, and people in your group are spending time thinking, why does it work? What's fundamentally different and why does it work? And I've spent the last 5 years asking myself the same question. And I think I've come up with a satisfying answer, at least for me. And I'm confident there's something there. We're going to see it. It just needs more time.
And something I want to add too, because we're talking about this in terms of maybe for manufacturing, is when we're looking at the areas where a machine learning solution can provide benefit, we need to think about kind of at what scale we want to utilize it. So if you want to make a certain solution more robust, it can persevere to local perturbations within an environment. That's something you can probably model as part of your manufacturing process, because you know kind of maybe what those limitations are going to be or what the bounds are, and at least train it or develop it to work within that scope. Whereas if you want it to be something that can more readily adhere to more global changes to a space. So this is the mom and pop shop that needs to change around their robot arm system for one manufacturing line versus another. That's a very different type of ask from a machine learning solution, but may be more of the value add to see it find its way into industry. And some of this what we see in some of the ARM Institute projects, where they may be approaching it from getting one solution that can maybe transfer between multiple different types of robot systems or different applications, or just really operating within those robustness challenges for a particular application. And there's probably something there of, what does the industry actually want to see where robotics can add something that some of their traditional automation solutions don't currently have.
Okay, thanks. I think you all touched.
Maybe I'll just respond to Matej. So
go for it.
I mean, it's funny, your example of the motor driver, that's a test for me, right? Like, do I believe that we're actually going to replace our motor controllers with RL? I hope not. I mean, what I would love for us to discover that, like, having some extra nonlinear terms in the low level could somehow, do better or whatever. But if I have to, every time I deploy a motor controller, I have to run a million simulations, that's bad news. I mean, I hope that the process will be, maybe RL will open up our eyes to something, but then we learn something and there's science happens and somehow we compress that understanding back down into a very transferable, compact, doesn't require massive simulations in order to get a lot of the benefit, right? Because I think the cost, when we were talking about cost a minute ago, I wondered if you meant cost in terms of AWS bill, right? Because there's a cost there too, right? And I don't want the cost of my motor amplifiers to incur that cost, right?
I strongly agree that there are hopefully interesting things we can do, that it's not going to be just a policy that's just a fully connected MLP and then you just train it for enough steps and that's it. That there will be those nonlinear terms. Maybe there's going to be those nonlinear terms that will be trained as part of the policy, but will be inspired by our domain knowledge and by our knowledge of physics, and that would be fantastic. But it's this seductive. I think the well-known who wrote the famous manifesto about it's this seductive thing that scientists want their domain knowledge to matter, but ultimately the only thing that matters is just better search, better general search, and better general learning algorithms. I think, was it Rich Sutton, the famous manifesto? And to be honest, I've been running into that with the manipulation work, the in-hand finger gating thing that I mentioned today, and a lot of what we presented today is model-free RL. But that's not because we didn't try what we thought were clever things inspired by knowledge of grasp, mechanics. But ultimately, those didn't work. It was just, and there's something about also these reinforcement learning methods. The random exploration, I think, turns out to be incredibly powerful. Anytime you start biasing the random exploration based on your domain expertise and your domain knowledge, we have more often than not found it to be counterproductive. That just throws off the optimization. So much to my chagrin, a lot of what we tried to put in as domain expertise in grasping and manipulation ended up being counterproductive, and only with very light touches, Model 3RL ended up doing the trick. At least in simulation, we'll see how it transfers. I agree with you that domain knowledge will matter, and we'll find ways to put it in, and it will make things much faster, much more efficient. It's not so easy, though. We have to find the right way to use that domain knowledge, and it's harder than at least I thought it would be.
But if Newton told you that here's your recipe, I've understood classical mechanics, you take a MLP that's this big and you fit it to your data, then where would we be today, right? I mean, there is something about levels of maturity of the field. I think what we're saying, I think RL is a great tool when our scientific understanding of the problem is not sufficient. It can help us explore those boundaries. But I would like to think that we will continue to compile our understanding into very general, practical things, right? That's just, as the field matures, right? I mean,
yes,
I agree. Yeah.
I mean, yeah, do you believe in systems science or not? It really becomes part of the question here, right? If you believe in systems engineering and systems science, then you want understandable blocks that you can actually interrogate and put together in novel ways to build more complex, more capable systems. And I think, RL, some of these deep learning techniques make it difficult to do that reliably. I mean, if I was going to complain about using the ML tools for solving some of the perception problems, it's that every time we go tweak that perception problem a little bit, we have to go train, and training is not cheap. It's much cheaper to go systems engineer and put together really complex blocks that we understand the performance boundaries of to build bigger, newer systems.
And bringing the problem back to manufacturing, right? We have been producing millions of products with today's technology, right? Robots today, they last forever. They work very well in repetitive tasks where you have low mix, high volume. That's solved, right? So low mix, high volume, today's technology is perfect. Now you reduce the scope to, okay, what if I have a little bit more variability? There's still, computer vision works quite well. You can find ways to separate the parts so that your machine can find them easier, so you don't need to rely on deep learning. So the use case for where you really need flexibility is much more narrow than the entire field of manufacturing, right? So we also have to be conscious about that. There is definitely, as I said, a lot of advantages when things are not easy to model, like when contacts, as we have here alongside in all the presentations, right? The contact dynamics are super hard, but still the fact that you can explain something means a lot, right? When we think about manufacturing, the explainability is usually one of the roadblocks that we'll avoid, even if the system is great. A technician should, right? These are the non-functional requirements of a system, right? A technician should, with very low, not necessarily a PhD in robotics, should go there and be able to fix something, right? If something is broken, right? Like my forklift hit my system and now I am 2 millimeters off. Can I calibrate it again, or nothing works, right? This kind of use cases should be able to, should be addressable.
This is a very interesting conversation, and indeed, I just would like to kind of go more in depth in some of the points. In a sense, I mean, for example, Matej is saying that in his opinion there is not such a huge gap, or because it takes time, right? And someone might think that the gap is there, but in both cases, I mean, even to reduce this time in order to get to what academia is producing, to get it into the industry, or to merge the gap, I mean, is it possible to define metrics, machine learning metrics, or evaluation methods, benchmarks, to really reduce this time that academia research can go into industry? I mean, is it even feasible to think to have some common benchmarks, and if yes, do you have any? And I was kind of impressed when before from said that, I mean, in his company they don't care really about the method they use, right? They have very specific criterion to decide if a method is successful or not, right? And whatever matches that criteria, then they are happy with that, right? Is it even possible to have something similar for both academia and research? Of course, in some sub areas of it.
Yeah, I think there's a lot of questions that come down to for evaluating ML that solutions that aren't in other solutions. Like, do we need to start characterizing what the systems were trained on? You know, how much training they have, or to what fidelity of training, or you know, what data they've been trained on versus the data that they have been given, or the data objects that they've been given to grasp. You know, for some like algorithm testing. Being able to characterize that element so you could actually do a comparison of one solution versus another and put them under the same amount of training into the same task set. I mean, even being able to quantify those elements is very, very tricky unless you're in a really, really bounded space where you're only a few dimensions. But all the problems we're talking about here are very high dimensionality issues. So I think a lot of it starts there of knowing how to even quantify some elements of the solution, because otherwise there are existing manipulation benchmarks that are more focused on maybe singular portions of tasks, and maybe it's a matter of just inducing some variation into how those benchmarks are performed that would intentionally stress a machine learning or some other higher robust solution. At the moment, I'm not aware of any particular benchmarks that are specifically aimed at, kind of flexing a machine learning solution versus another. But I think there are ways that we can tune some of our existing ones to match.
I mean, there's occasionally these grassroots efforts to start, to agree on the rules of the game, right? Of like whether it's rearrangement, or there was the DexNet, and Rob Platt and everybody were trying to put together something, and the challenge seems to always be that everybody wants to have a slightly different set of rules. Like some people want to go from only RGB. Someone says I want depth. There's nobody. Someone says I want a 2-finger gripper. Someone else says I want whatever. And I do feel like we have to. Well, it would be a natural evolution of the field to sort of agree on something and have everybody hammering on similar problems and sharing hardware. That would be awesome. And I keep feeling like we're getting close, but it hasn't quite happened yet.
I mean, from the point of view of the final goal, right? From I'm a manufacturer, will I adopt this technology or not? Metrics like number of successful picks, right? Doesn't matter, right? It matters the overall throughput of the system, right? So how do you achieve it? It matters the overall throughput with the ROI that I can afford, right? So how do I achieve it? I really don't care. And that's the difficulty, as you're mentioning in this field, right? Because even the same problem of this Amazon challenge, right? It was solved in so many ways. Like Kindred solved it completely different other approaches, right? So you can, I think fixing a set of grippers and robots and cameras will really reduce it will not reflect the heterogeneity that you see in manufacturing, where everything is absolutely different. At the same time that I say that, I think that more subjective benchmarks where, okay, you can compare two methods, but you cannot yet really say they are better from another. One may be cheaper than the other and achieve slightly worse performance. But the moment that a sensor gets, some company finds a sensor that is cheaper, that solution will be better, something, right? So efforts like what NIST is doing with this assembly board, I think it has value, because at least there are some sense of, for some tasks like assembling wires or connectors, there is some learning to be made, but it's not as easy as say this method is better than this other, like you do in computer vision. All the details on what is your hardware, what are your limitations, in which conditions did you test it, this also matters.
Yeah, I mean, there's also the matter of how much data do we need to collect to actually say that we have adequately benchmarked that solution. You know, achieving statistical significance when you're using static stimuli is already hard enough to do it in academia because we've all read papers that have an N of 6 or whatever, and you know that's just, it is what it is. Where now, if we're talking about something that is intended to be robust and work in all of these various conditions, that number of test conditions and repetitions you need to do, obviously it skyrockets astronomically, which is why a lot of this, we do a lot in simulation, do a lot of training in simulation, a lot of testing in simulation, but being able to do that physically to validate, and not saying that necessarily needs to be as comprehensive as you would in simulation, but maybe there is some agreed upon minimum set, whether it's, you know, bounding edge cases and something in the middle. I know some of the talks for today's workshop talked a little bit about that. You know, setting some defined criteria to say that the amount of testing we've done for this particular benchmark is sufficient. Finding where those are, you know, that's a very big open question, but that we really do need to be doing some physical validation of any of this to really qualify it as being able to work in the real world.
That would be awesome, Adam. Yeah. I think it's really hard, right? Because the last product that I was working on when I was working at Siemens was flexible grasping on PLCs. Right? And how do you test it, right? And like the most difficult thing of my job was explaining the taxonomy of pin picking, because it's hard, right? Can your system pick up this object? I don't know, maybe, right? It's if I have seen it, yes. If it's something completely novel, maybe not, right? Until I try it, right? So there is a lot of trial and error. It would be great to find a set of objects and conditions that are representative for everything that is out there. I don't know if it's feasible.
You may be able to find minimum agreed upon sets for, you know, 80% of, you know, I'm going to add more and more qualifiers to further narrow it down. But yeah, it's the same thing with, you know, the YCB object set, as widely used as it is your kind of base level set of objects for if you're working in the kitchen, if you're working whatever their, you know, all the different kind of subgroups are. But it is something that is now very widely propagated throughout the world, used in, I'm sure all of our labs probably have a set of YCB objects. If not, we can provide you one from the Nerve Center. You know, similar types of object sets for, you know, maybe more narrow manufacturing applications or whatever the application is, whether it's gathering different manufacturing widgets. You know, obviously this becomes a really, really difficult thing to bound because for manufacturing, it can span so many different, you know, different areas. But certainly things like the YCB set, you know, they probably don't currently cover a lot of those, the kind of nuances with some of those objects, and in particular don't cover really anything yet with, you know, using objects to perform a task. We were talking about like insertions and screwing and things like that, where things like the NIST task board start to get us towards there, which is great. But you still have to do that kind of variation induction in order to really test an ML solution.
I don't know. Go ahead.
So I was just going to say, I think, you know, all of those standardized test sets are great and obviously help unify how people understand capability of these various different approaches. But, you know, the ultimate adoption with actual users is only going to happen when you can actually do meaningful proof of concepts and demonstrations, you know, in their facility with their parts. And that's always going to happen. And those people, especially when it comes to doing, you know, business critical manipulation or any robot deployment, they're going to be conservative. And so it's going to take a while for these technologies to move out.
I think that's a great point. And, you know, on the benchmarks and the standardized object sets, I mean, I kind of honestly tend to take the opposite view these days, in that I'm no longer such a believer. You know, the YCB is fantastic. We have one. I think it was a great effort. I have yet to see a paper that uses the YCB as it was intended, namely by showing their results on the entire set, or at least on some logically coherent subset of the YCB. Everybody, or maybe I've seen the wrong papers, people will select arbitrarily 6 to 10 to 15 objects out of the YCB and show 90% success on them. And how were those selected? Well, it was the set that their method works 90% of the time on. And everybody does that, right? And that defeats the purpose. But, and you know, there was a question earlier, you know, and then given that we don't really benchmark and it's very hard, how does industry know when technology is ready? And I think this goes back to Al's point. Ultimately, the only thing that matters is, are you saving somebody money? Are you alleviating somebody's pain point? And they don't know. They won't know when technology is ready for that, because they don't even know to look for this technology. They don't care what the technology is. They couldn't care less what the technology is. They just want their pain point alleviated. And I think what happens is that the gap gets bridged when somebody who knows the technology goes looking for applications and goes looking for domains where people don't even know that they need something, or aren't looking at robotics, right? So a roboticist goes looking at domains and eventually finds a domain where the technology is useful and does the additional systems work and engineering work, and then it gets deployed. And the only metric benchmark that matters is you're saving somebody money.
A good example, for example, is recycling robots, right? These are great example where ML is already making a big difference. What is you get the peak brown, nothing happens, right? It's much better than today's systems. Things are easy to detect. If you break them, they're already broken. So perfect use case for technology, right? The other case is what happened with this Pepper robot, right? The humanoid robot from your previous mother company, Al, that they build the company before the the application, right? So it's this kind of build it and they will come. I don't think it works in robotics. You need an application first.
Yeah, I mean, the Pepper story is actually much more complicated than you might imagine. But I think that's a really good point. You know, we've been lucky, right? You know, we were able to spend all this time doing basically research on legged locomotion and develop very significant public awareness of what we did and sort of interest in what we were doing. And for us to commercialize has been an interesting experience, because we do have some customers who just want a Boston Dynamics robot, and they don't actually care yet whether it's actually productive for them. And so we get our foot in the door with a lot of potential customers very easily, but that only gets you so far. And you have to then actually show them that it really does work and penetrate to the operations part of their organization, and not just the innovators, researchers. And so, you know, I think this is really hard.
Maybe just to conclude the topic on the metrics and so on, we can use also the question that are on the chat from Megan and Jeremy, that they were asking how is industry supposed to know when the technology is ready for integration? And the follow-up is how is industry supposed to know which technology in a field of competing technologies they should be pushing for integration?
Well, to the point of Al and Mate, I don't think this really matters, right? It's not like you have a screwdriver and you're looking for screws, right? Or a nail, you have a hammer and you're looking for nails. You have a problem and you will look for the best solution to solve it, right? Now, related a little bit to that, what probably as an industry we can do better is not just do these cool videos that work 1 out of 10 and post it out there and see that it seems that it works every time, but be very honest also with the capabilities of the technology. TRL3 is nice, right? It works, but then there is this valley of death, 3 to 7, where institutes like ARM are doing a very good job on maturing this technology and at least showing that this works in a representative environment. That brings you to 7. This 7 to 9 is also another huge step that you need to climb, like huge, right? So making a product is super hard. I have a lot of respect for people doing products in robotics. I'm now wearing that hat. It's super complicated, right? It's really, really, really hard to do a product in robotics. And at the end, you will use what probably if you have in this journey, you will have thrown 90% of the features and you just have the only one that really matters for the customer. And that's what you go with, right? Even going back, right?
Oh, sorry. I was just going to say that you can think about the metrics that matter at each kind of TRL bound, right? So from TRL 1 to 3, all of the metrics you're going to care about are going to be really nitty gritty. Where these are like the things that you would measure as part of in an academic lab, someone who's doing their graduate work. They care about how accurate their vision labeling algorithm was, or whatever it is, blah blah blah. Then as you get to 3 to 7, now you're starting to apply this more as part of a task or process of what does that underlying capability actually get you? Because now you care about the environment, you care about where the information comes from, where it goes to. And then as you get into 7 to 9, as you're just alluding to, Juan, now it's ultimately going to be like cost, savings. It's probably some push and pull between there that are all sitting on top of all of your previous metrics, but it doesn't matter when you get there, right? So even when we're talking about benchmarking or metrics as they go across those levels, they're going to be different along the way. So if we have methods that can span that scale, but with just different metrics that you care about at each phase, that would at least separate, what academics are going to care about while they're developing it, because they know that it's going to go into the realm that industry will care about it down the line. But we do have to have kind of a clear set of each of those.
I've almost said this from the last 5 speakers, but you say academics care about. And I feel like there is a fundamental problem here, which I think is a disconnect between academia and industry.
I cannot hear you, Russ.
Is that right?
I can hear you.
Yeah.
Okay.
Sorry, then it's just my end.
So, academics are not rewarded right now in any way. I mean, what would the normal incentive structure to have a benchmark or to go against those metrics? It would be like if it helped you get your papers published, or if it helped you get funding or whatever. But in any of those mechanisms right now, people are more rewarded to pick the 5 YCB objects that it works, or show some object that it didn't exist before. And that's going to end to put the one-time YouTube video on. I don't know if it's like science is broken totally, or if it's just like we're in that phase of our development for robotics right now. But I would say right now there is a big disconnect between what people are rewarded for in academia and what we're talking about throughout this conversation.
And I would argue that that's kind of fine, right? In academia, right? That's our role in the ecosystem to come up with ideas that might really have an impact 5 years down the line, or 10 years down the line, or 20 years down the line. If for things that can be commercialized by the end of next year, industry is way better set up than us. They don't have to, they have all their time to spend on it. They don't have to write grants, they don't have to write papers, they don't teach, they have big teams, they can build things faster. And that's what they're set up to do, and they're doing it really, really well. And we have our role to come up with ideas that are going to make a difference further down the line. And I think, the system works. It's, of course, and there are exceptions. Of course, there will always be, academics who come up with things that immediately have an impact. And there will be people in industry who do come up with amazing ideas that last for decades. But by and large, I think it's fine that we have our eye set a decade in the future.
Yeah, the danger nowadays comes mainly of the New York Times of the world, the Wire of the world, the Crunch of the world, that will take a paper and completely exaggerates, and then they do an interview and it's like, yes, of course, this will solve all your problems. It works in my video, right? So, but being realistic to unground that, maybe train more the public, right, on, hey, this robot that you see dancing is probably not using AI, right? It's not going to kill you. I mean, you know, it's good old-fashioned control that works very well, that takes a lot of time to tune. So doing that training and that kind of massaging our messages, I think will help towards that, in my opinion, right? A lot of times our claims are exaggerated when it comes to robotics, because it's so inside our brain, when we say so connected to science fiction, that we make a lot of assumptions in the near term, completely over-exaggerated. Well, and completely, I mean, this famous phrase on, we completely underestimate the long term, right, but overestimate the short term. I think that's happening for most of the robotic research.
I mean, I think it's a deep question. There are other fields that have moved fast, broken. I mean, computer vision is benchmark driven, right? You can't publish a paper in computer vision unless you compare against other benchmarks, and that field has done pretty well, I would say, right? So somehow robotics hasn't made that change, or it hasn't chosen that path. I agree with you that we need to be able to do big sky things, but I don't know. I mean, I'm fundamentally torn. Are we, like, we don't cite each other's papers, we don't read anything that was published, 4 years ago or whatever. Is that good? Like, we need to be able to explore quickly, or is it, are we really just doing such bad science that we could be doing the same aggressive thinking, but be a little bit better as scientists? I actually don't know.
Is it a matter of more intelligently identifying the gap that should be filled, right? So, I mean, you can make a better solution to modeling, contact modeling. I know that was something that was mentioned earlier, but, do you need to back up and ask the question, is this the gap that needs to be filled in order to have the impact at the industrial level? Because some of it, this is a totally different field, but in the response robot domain, all the controller interfaces for teleoperated robots, pardon my French, but they suck, and they've sucked for so many years. But at the same time, all of the academic researchers in like RoboCup Rescue, they're working on these really newfangled, crazy AI-driven, solutions that, as far as I can tell, are not going to see the light of day into that field in a very long time, because we still can't get basic obstacle avoidance for a two-dimensionally driven ground robot. Now, there may be like logistical reasons why some of that doesn't happen, but that huge gap is because are we not solving the right gap that would actually have an impact on the industry versus, maybe solving some other metric that, for whatever reason, has been noted as being important.
Adam, you guys just need to buy spots, but it's got the issue.
We're in line. Don't worry.
I think I can but to the underlying point there, and to what Russ was saying, I'm probably not the most cutting edge researcher at Boston Dynamics, but a lot of the stuff that I'm working on and the people I work with are spending their time on is stuff that is, years from appearing in our products, right? We are, they're also touching things that are going to appear in the next 3 months or 6 months. But we spend a lot of time reading old papers and reminding people, like for doing this manipulation stuff, I spent the last month basically reminding people how to do impedance control and, remote center compliance for peg and hole problems, because nobody remembers how to do that stuff anymore. And if you can't have that as a primitive, I don't care how fancy your ML thing is that you put on top of it, you're going to struggle to perform tasks meaningfully, right? You need that primitive capability that is just a well-designed local controller. And so I think there is, I can argue that, yep, science is broken or the robotics field is broken because of the incentives for the academics. And having been one, I've been a lot happier since I quit. I got off that treadmill and got on to, doing what I think is real work. And a lot of the real work is really focused on deciding which problem is actually important. And I think one of the luxuries that we had, especially when we were doing the contract work, was that, we had sponsors who cared about, who trusted us to tell them what was actually important to get to the type of demonstration they wanted to get to. And that let us really focus on moving the technology forward to the point where, 10, 12 years later, we can actually sell a walking robot that people want to use, or at least they think they want to use. Mm-hmm. I think manipulation, needs to follow a similar trajectory, but that's also my selfish Boston Dynamics interest that we will succeed at making manipulation just work.
I mean, talking about these long-term ideas that academia can provide and what is important and what is not important to research on, just to kind of inspire the community. I'd like to ask to each and all of you, what would be an impressive result that you would really like to see, that you think is missing, and you would be really impressed if you see, that robotic demo, that paper, whatever. So in other words, what could be a moonshoot problem that we should try to achieve in robotic manipulation as a community overall?
I have my favorite picks for sure, but I think for anything I pick, I could get a really clever, like we call them robot whisperers around here, that could program a state machine that would get it done pretty darn well with enough hours on the robot. Or we could get a one-time video of an RL search that discovered something. So I think asking only what would be the demonstration that we want, I think isn't enough, right? Somehow it has to be qualified by how generalizable that approach was, how many hours of simulation it took, or something like that needs to be added on to the question, I think, to make it well-defined.
So a little anecdote, I forget how many years ago, it was probably 4 or 5 years ago, Raybert did a TED Talk, and it was the first time we showed a spot robot with an arm in public. And, the robot was going to go pick a Coke can up off of a table and bring it to him. Pepsi can, I'm sorry, this is Mark. No Coke, Pepsi. I think we spent almost a month of time, calendar time, with about 2 or 3 people working on that demo. And it took like 2 days to make the demo basically work. But to run through all of the reliability issues to get what was a 1-minute demo to work at a level that we were all comfortable putting it on a TED stage was pretty onerous. And, I think we said, gee, until we can do this 100 times in a row without, messing up somehow, we're not going to ship it. So, yeah, the TRL level matters, and it's not the specific demo. It is the set of capabilities, features that make a demo possible that have to all hang together in a reliable way. I'm sad that the search and rescue sort of robotics field hasn't made more progress than it has in the last 10 years, because I think there is a relatively benign, or at least well-defined problem that involves, basic locomotion, mobility over some terrain, and some pretty rudimentary manipulation that we as a field should be able to deliver on.
If I can add on to I think it was Russ's comment about, maybe a demonstration isn't enough. It's a matter of making, I don't know, is it a matter of making people care about more than the single demonstration? I don't know how we do that. But, at the end of a project, there's always some final demonstration where they show it work a couple times. And then you read the report and hope that they did 10, 20, 30 repetitions of it or in X number of conditions. That's not the sexy part of it, but it is the more meaningful part. So I don't know if it's a matter of just getting people to ask the right questions to be for adoption or to be impressed or whatever it is, but it's somehow highlighting maybe more just the importance of that aspect as opposed to just demonstration.
Yeah, I always like to compare these demos like when you see a cowboy riding a bull, right? It's like, okay, this is the cowboy riding the bull, and then the beast is tame, kind of, right? But it's not, right? It will at some point kick him out. But if you just take that 10 seconds or that minute, you just really see that you're in control, but you are not, right? It's like we are kind of taming a process here. Is seen on the long tail, what are the limitations, making it work 24/7 for X amount of time, in the conditions that are meaningful, and that's the impactful thing, right? Is things that are meaningful. Well, I want to see really a peaking system that works reliably for every single thing that I throw in any single lighting condition with the same dexterity that a human, which is part in the same throughput. But that's not super far away. I want to see a self-driving car. I mean, that is all over the news. I want to be in one. I mean, not just read it, but be in one. I think that's something that seems still like a moonshot to me.
True. And yeah, I mean, this is more a comment than a question, but yeah, I mean, I also agree of this reliability, right? That we want to have these systems working 24/7, or having these, we'd like to have these things not working just for that demo, for the video, but reliably. But I think also that for how maybe academia is, that there is always this rush of submitting the new paper, having and publications and so on. That's exactly the part that nobody really wants to do in academia, right? I mean, and as I said, for having that simulation, they had to spend an additional extra month. And because they had a specific target, that was the showing the robot in the TED Talks, right? It was very important. But if there is no such a stimuli, nobody's really gonna do it. Not nobody, but the average researcher, right? And probably this is a problem of the overall system.
I don't think it's a problem. It's just not our place in the ecosystem. We are in the marketplace of ideas. We are not well set up to do the reliability part, unless it's something intrinsic to the idea. Maybe there's something intrinsic to the algorithm that doesn't lend itself to repeatability. And then somebody else will come up with a better idea that there's nothing intrinsically wrong with it. But it's just not our place in the ecosystem to spend the time to do that. And it's fine. We are optimized for something else.
No, but we're supposed to be scientists, right? And so we're supposed to increase the knowledge base of the world, right? And somehow I think I want to be able to think about crazy things and try something and publish it if it was a crazy idea. But I also want to add to the knowledge base. I want to continue to build a foundation of understanding, and I think that's where we're failing right now. I mean, I not everybody, but I think overall the quantity of papers that get published compared to the growth in the understanding of the field, I think is out of whack.
What we can do about that maybe is be better reviewers, right? You review a paper and you look at the validation that they have compared to the claims that they make, and we can all ask ourselves, does this set of experiments support the claims? And then if we find that their validation doesn't cover certain cases, we bring that up, and we do a better job of not letting through papers that don't properly validate their claims. But I don't think that is a specific, one-size-fits-all benchmark that all papers have to go through. It's on us to put in the time as reviewers to understand specifically to each paper what's the right way to validate the claims, and are they meeting the bar or not?
I mean, I would actually, we should sign up and do a longer conversation. I don't mean to take away from the manipulation thing, but I think that's a hard question too.
It's a very hard question. Back when I was an academic, I used to serve on the IJRR board, and man, that was a hard job. And just not fun. I mean, I think it served the community, but man, no reward and lots of suffering and lots of angry people. To the research question though, and one of the problems I have with the ML stuff is because the ML stuff is potentially very black boxy, it's very difficult to transition it or to know how much you have to mature it as an academic, right? To be an academic and have an idea about something that's provable, whatever, some traditional control thing that has, known input-output behavior and known bounds on performance, you can transition that thing to industry, and industry can then progress it in a rational, logical way. We don't have that science for these trained systems, right? We don't know how to take something that one of you guys built in your lab and turn it into something that is more mature and more robust in a systematic way. We have to just go start from scratch, essentially. And so I think that's one of the weaknesses of the RL ML techniques.
There is also, like, if you take a look at the field of industrial automation, which I don't think we do a good job to teach it enough in the US, but if you go to countries like Germany, that's also core. This has evolved for a lot of years, right? There are a lot of standards around. There is not a similarity with industrial autonomy. Right? We don't know what to test. We don't know. We don't have tools, really. It hasn't really evolved. Or I don't know if this is even a field, but it will be required if more and more data-driven approaches, AI, are moving into manufacturing.
I think that's a very good point.
And I would go back to the example of particle filters for SLAM, right? It's a probabilistic approach. As such, you can never have hard guarantees. You can have probabilistic guarantees, which arguably may or may not be useful. And ultimately, the only guarantee you have is that, look, it just works. It's a probabilistic approach. It worked all the previous 10,000 times. It's going to work this time as well. And right now, based on such a black box approach with no guarantees, people are building companies that are incredibly successful in the marketplace. So one person's black box is another person's probabilistic approach, which won't have proofs. It just works.
All right, with this, we are actually a little bit over time. I mean, we had many more questions to ask you guys, but the discussion has been so interesting just with these questions, and I really would like to thank you all. Some of you stayed here with us for so many hours, so I think we can give a round of applause to all the speakers in this panel session. I think it was very interesting, and I really want to thank you. And with this, I declare the panel session over, and I hand the talk to Megan, who is gonna just wrap up the workshop with final comments.
Thank you.
Thanks.
All right, thank you guys so much for coming to the workshop today. I want to thank all of our speakers so much for all of their great talks and for also participating in the awesome panels. If you're interested, we are going to continue talking on the Slack that we made for people who are working on AI for manufacturing robotics, but your manipulation people are more than welcome to join as well. And also feel free to check out the website we created to start to get the community talking to each other with regards to AI for manufacturing. And then also the videos for all of the talks for this workshop will be posted sometime later this week on the website. So thank you all for coming. If you have any questions for any of the speakers, just feel free to email them or reach out on the Slack. We'll see you maybe next year, who knows? But thank you all.